So in this session, we are going to talk about analytic function or holomorphic function, regular function. We are also targeting for singular point, Cauchy-Riemann equations. Cauchy-Riemann equations are also called CR equations. And then harmonic functions. And then we will learn how to find harmonic conjugate function. So we are going to talk about these contents today. So besides this, you have to recall all the formulas of differentiation that you have learned from your previous courses. So for now, we need to just know these 8 rules. That is, differentiation of a constant is 0. Differentiation of a sum can be found by this way. Differentiation of a product, differentiation of a quotient. We also know that ddx of x to the power n is nx power n negative 1. So these formulas need to be recalled. So before talking about analytic function, we have to know about complex valued function. We know that complex number can be written in 2 forms, rectangular and polar. So rectangular form is z equals x plus yi, and the polar form is z equals r e to the power I theta. We also know that any complex number can be thought to be a point. That is, x plus yi is nothing but x comma y. Similarly, z equals r e to the power I theta. This is also a point r comma theta. So this part is known as the polar form of complex number, and this is the rectangular or Cartesian form of complex number. So based on these 2 forms, we can think about complex valued function also. So complex valued function can be written in rectangular form, or we can also write complex valued function in polar form. So complex valued function is normally denoted by f of z equals u plus vi. So here you can see we have 2 parts, u and v. U is the real part and v is the imaginary part. So depending on the rectangular form or polar form, this u and v can be a function of x comma y. This u and v can also be a function of r comma theta. Complex valued function is also denoted by w equals f of z. So w equals f of z equals u plus vi. So u and v can be x comma y or r comma theta. So any complex valued function can be written as u plus vi. So remember, this is the real part and this is the imaginary part. So our first target is what is the definition of analytic function. But before that, we have to know about differentiability of complex valued function. So what do we mean by differentiability of complex valued function? So differentiability of complex valued function depends on the limiting concept. So let's say we want to know the derivative of complex function. So if f of z is a function which is a complex valued function where z is x plus yi or r e to the power I theta. So the derivative of f of z at z naught is denoted by f prime of z. That is the first derivative of the complex valued function f of z. So this can be defined by limit delta z tends to 0 f of z naught plus delta z negative f of z naught over delta z. So this is the definition of derivative of complex valued function. So you can see that whenever we are targeting for the first derivative of complex valued function f of z at z naught, it can be defined by the limiting concept, that is limit delta z tends to 0. In numerator you have f of z naught plus delta z negative f of z naught over delta z. So the derivative of f of z at z naught will be defined by this way, but this limit should exist. So we can say that provided the limit exists. So this is the definition of derivative of complex valued function. We can write f prime of z as df dz, or we can use an alternative notation. You already know that any complex valued function f of z can be written as w equals f of z. So if the derivative is defined by df dz, then we can also write dw dz. We can also use alternative notation. Df dz is f prime of z. So dw dz will be also w prime. So we can use any notation, whatever we like. So we can find the derivative of f of z at any point. So suppose we want to find the derivative of w equals f of z at z naught equals 1 plus I. So in that case, at first we have to find the first derivative, that is f prime of z, or we can say w prime, or we can say dw dz. So if we want to find the value of the derivative, so it can be denoted by this way: f prime of 1 plus I will be dw dz 1 plus I. So we can use this notation also. That means we are targeting for the value of the first derivative. Suppose for now I am writing directly. We have a function, for example, f of z equals z squared. So you know that ddx of x squared is 2x. So similarly, ddz of z squared will be 2z. That means the derivative of f of z will be 2z using this formula: ddz of z power n, that is n z power n negative 1. So we want to evaluate the first derivative of f of z at, let's say, at z naught equals 1 plus I. So we will just plug the value here, 1 plus I. That means where we have z, we can input 1 plus I. So we are getting 2 plus 2I. So this is the value of the first derivative of the function f of z equals z squared. We can also write in this form, that is dw dz at 1 plus I. So you can use any notation, whatever you like. So we are targeting for analytic function. We want to understand the definition of analytic function, but before that we have to know what is the definition of derivative of complex valued function. So the derivative of complex valued function f of z is denoted by f prime of z, that is equal to limit of this one when delta z is approaching to 0. So here now we can discuss about analytic function, or we want to know the definition of analyticity at a point. So what is analytic function? So let's say we have a complex function w equals f of z. So this function is said to be analytic at any point z0 if this function f of z is differentiable at z0. That means we can apply this definition. So analytic function deals with this definition also, that is f prime of z equals this one. But besides this condition, this function should be differentiable at the neighborhood of z0 also. A function w equals f of z will be analytic at z0 if that function is differentiable at z0. But this is not the only condition for analytic function. This same function f of z should be differentiable in the neighborhood of z0. So a function is analytic if f of z is differentiable at z0. That means at z0 we will get f prime of z0. This is obvious. But besides this, that function is also differentiable in some neighborhood of z0. So I have used a term neighborhood. You have to understand the definition of neighborhood now. So perhaps you can remember that we know modulus of z negative z0 less than rho defines an open disk. It defines an equation of circle at center z0, and it will be an open disk. Since we have this inequality less than, so it means we have this inside region. So in this region, that means within this region, there have many points. Let's say z1, z2, z3, z4. We have infinite number of points here inside this region, inside this circle. So z1, z2, z3, z4, all these are the neighborhood points of z0. That means if the function f of z is differentiable at z0, that function is also differentiable at z1, z2, z3, z4. That means that function is also differentiable in the neighborhood of z0. So whenever neighborhood term is coming, you have to think about open disk. If a function is analytic, remember the function is differentiable at z0, the function is also differentiable in the neighborhood of z0. So analytic function is defined by this way. That means analyticity is a neighborhood property. Suppose A function f of z is analytic in any domain D. So if the function is analytic throughout the domain D, then that function is also called holomorphic function. Holomorphic function, analytic function, regular function are same. If the function is analytic throughout the domain D, that means inside D, whatever points we have, Z0, Z1, Z2, Z3, up to Z infinity. So for all that points, the function is differentiable. So that's why in that case, that function f of z is also called holomorphic function or regular function. Suppose we have a domain D. This is inside the complex plane xy. It is called z plane, where x-axis is the real axis and y-axis is the imaginary axis. The function is differentiable at z0. The function is differentiable within this region. That means the function is differentiable at all points inside this circle. Then it is called analytic or holomorphic or regular. But if the function is also differentiable at all points in the complex plane, then that function is called the entire function. So if a function is analytic at every point z in the complex plane, then that function is said to be an entire function. So for example, any polynomial function, let's say f of z equals z squared plus 5z plus 6. This is a polynomial function. F of z equals z cubed. This is also a polynomial function. F of z equals just a constant 1. This is also a polynomial function. We may also have f of z equals z to the power 4 plus 5. This is also a polynomial function. So in general, we can write that polynomial functions are f of z equals a n z power n plus a sub n negative 1 z power n negative 1 plus up to a1 z plus a naught. So here I have written a sub n negative 1, a1, a naught. All these are just a constant, like 5, 6. Here we have 1. You can think about this is a2, a1, a naught. So this is the general form of polynomial function. So all polynomial functions are entire function. That means all polynomial functions are analytic. If the function is analytic throughout the domain D, then that function is also called holomorphic function or regular function. If the function is analytic everywhere, then that is called entire function. So which functions are entire function? Any polynomial function are entire function. So polynomial functions have the general form, this one. For example, you can think about this, and this. So this is called 0-degree polynomial function. It is 2nd-degree polynomial function, 3rd-degree polynomial function, 4th-degree polynomial function. We can think about higher degree polynomial function. Let's say we have 6 z to the power 5 plus 3 z squared plus 1. So this is also a polynomial function, and it is called 5th degree. What is the definition of degree? Degree is the highest power of z. You can think about this function. Here you have z power 0, z power 2, z to the power 5. So z power 0, z power 2, z power 5. The highest power is 5. So depending on this highest power, the name of this polynomial function is 5th degree polynomial function. Depending on the highest power of z, we call what is the function. That means it is 4th degree polynomial function. It is 3rd degree polynomial function. It is 2nd degree polynomial function. So the main concept is any polynomial function is entire function. That means it is analytic in the complex plane. So now let's talk about another function which is called rational function. For example, we can think about f of z equals 1 over z. We can think about f of z equals z squared over z negative 1, z positive 2i. So you can see that any rational function has the property that it has a numerator and denominator. The numerator is a polynomial function. The denominator is also a polynomial function. So you can see here 1 is a polynomial function. Z is also a polynomial function. But whenever we have P over Q form, then that function is not the polynomial function. It is called rational function. Similarly here, f of z equals z squared over z negative 1, z plus 2i. So in numerator, we have polynomial function p of z. In denominator, we have another polynomial function q of z. But it is called rational function. So rational functions are also analytic, but there is a point where the function f of z equals 1 over z is not analytic. There are 2 points for this function where this function is not analytic. So how we can understand this concept? So let me discuss. Think about here 0. So 1 over 0. So 1 over 0 is undefined. So that means if z equals 0, then this function will not be defined. It means the function will not be analytic because the function will not be differentiable at z equals 0, because at the first side we are getting 1 over 0 that is undefined. Similarly, for the second example, we have the denominator z negative 1, z plus 2i. So if this denominator becomes 0, so z squared over 0, that is undefined. So that means we can solve, that is z negative 1 equals 0, z positive 2i equals 0. So actually we have z equals 1 and z equals negative 2i. So if we input z equals 1 here, 1 negative 1, 0, 0 times something, 0. So something over 0, that is undefined. So that means at z equals 1, the function is not defined, which means the function is not analytic. In other words, we can say the function is not holomorphic. It is not regular. It is not differentiable at z equals 1. Similarly, if we input z equals negative 2i here, so negative 2i plus 2i is 0. So 0 times this one, 0. Something over 0, that is becoming undefined. So again, we can say that for this function, we have exactly 2 points where the function is not defined, and therefore the function is not analytic. So we have mentioned earlier that for polynomial function f of z, we have seen that this type of functions are entire. That means all polynomial functions are analytic in complex plane, but all rational functions have some points where the function is undefined. So that specific points are called singular point. That means z equals 0 is the singular point for this function. Z equals 1 and z equals negative 2i are singular points for the second function. So in summary, we can say that any function that is of the form p of z over q of z, it is known as rational function. So this rational function will be analytic except these points. That means if we solve denominator not equals 0, then we will get the values of z. So at that point, the function will be undefined. Therefore, the function is not analytic. But other than these points, the function is analytic. So remember, any rational function has some points where the function is not analytic. So the points where the function f of z fails to be analytic, that points are called the singular points. That means if I ask you, find the singular point of f of z equals z squared over z negative 1, z negative 2i squared, then what we will do for finding the singular point, we will apply this technique. So we'll solve for denominator equals 0 or not equals 0, say. So denominator equals 0, that means in denominator portion we have z negative 1, z negative 2i squared, that is equal to 0. So z negative 1 equals 0, z negative 2i squared equals 0. So we are getting the roots, that is z equals 1 and z equals 2i. So these 2 points are the points where the function is not analytic. Except these 2 points, the function is analytic. But these 2 points are called singular points. So remember, the definition of singular point is the points where the function f of z fails to be analytic. Let's say you have f of z equals 5z over z cubed negative 1 plus I. So for finding the singular points, the technique is you have to use denominator equals 0. That means in denominator you have z cubed negative 1 plus I equals 0. And now you have to solve this equation. So how we can solve? We know the de Moivre's theorem that we have learned in earlier sessions. So we have learned that there will be three solutions, namely zk. So for the three solutions, we can input k equals 0, k equals 1, k equals 2. So that is how we can find all the points. So at that points, the function is not analytic. So up to now, we have learned what is the definition of analytic function, singular point, and this is the time to talk about Cauchy-Riemann equations. So Cauchy-Riemann equations. These equations are named after the two mathematicians, Augustin Louis Cauchy and Bernhard Riemann. Augustin Louis Cauchy was the French mathematician and Bernhard Riemann was the German mathematician. So now we know this one as Cauchy-Riemann equations. So what are Cauchy-Riemann equations? Any function w equals f of z can be written as u plus vi. So this function will be differentiable at any point z equals x plus yi. Then the Cauchy-Riemann equations will be. Just try to focus here. I have written two equations, the first one and the second one. So I have used one symbol here, that is this one. So this symbol is called the partial symbol. It is also known as partial D, or we can say it is curly D, or we can say it is curved D. That means there is a difference between ddx and this partial d partial dx. This is known as ordinary derivative, and this is called the partial derivative. So suppose we have a function f of x comma y equals x squared y. So this function has two inputs. That means we have a function where x and y are inputs. We have two inputs this time. These are called function for several variables. So if we try to find the first order derivatives, then it will be df dx, df dy. So that means we are differentiating f. So the function f is x squared y. So remember, whenever this symbol is present, at that time you have to focus on this variable. So this variable is x. So except this variable, other variable will be constant. So that means inside the parenthesis we have x squared y. So x is variable but y is constant. So y can be pulled out. So ddx of x squared. That means now we know that differentiation of x squared is 2x. So finally, we are getting 2xy. Similarly, we can also find the derivative for y, and the function f is x squared y. So this time we are differentiating with respect to y. So now have a look on the inside quantity. So we have x squared y. Since we are differentiating with respect to y, then x will be constant. So the constant ddy of y. So we know that ddx of x is 1. So ddy of y will be 1. So the partial derivative of y with respect to y is 1. So x squared times 1. That means we are getting x squared. So this is what partial derivative is. That means whenever we are differentiating in terms of x, then y is constant. Whenever we are differentiating in terms of y, then x is constant. So we can pronounce this symbol as partial d, curly d, curved d. We can also say it is del. But remember that there is a difference between d and this d. So we are trying to understand whether a function is analytic or not. The Cauchy-Riemann equations are du dx equals dv dy and du dy equals negative dv dx. So these are called first order partial derivatives of u and v. These two equations are called the Cauchy-Riemann equations. This is the first one and this is the second one. So a function will be analytic if this function satisfies these two conditions, which are known as Cauchy-Riemann equations. So any function f of z is written as u plus vi. So w equals f of z, which can also be written as u plus vi. So where u is a function for x comma y and v is also a function for x comma y. So you can also remember that whenever I have started the session, I have also mentioned that u and that v can also be a function for r comma theta. So u and v can be function for x comma y or r comma theta. So this is the rectangular form and this is the polar form. So depending on these two concepts, we can think about, we have Cauchy-Riemann equations in rectangular form. We have also Cauchy-Riemann equations in polar form. But for now, we are trying to discuss Cauchy-Riemann equations in rectangular form, where u and v are the functions of x comma y. So a function is analytic if it satisfies these Cauchy-Riemann equations. So we have also another condition, which is known as the sufficient condition for analyticity. So let me write that one. You can think about, we are coming from the backward portion. So let's say we have the functions u and v, which are functions for x comma y. So u and v are continuous functions. U and v have the partial derivatives du dx, du dy, dv dx, dv dy, and it satisfies the Cauchy-Riemann equations, that is du dx equals dv dy, du dy equals negative dv dx. Then we can say that the function f of z that is formed by u plus vi is analytic in some domain D. So you can think about these two conditions are vice versa. That is, if we have f of z equals u plus vi, if this function is analytic, then it satisfies the Cauchy-Riemann equations. And suppose now we have only u and v. If u and v are continuous, if u and v have the first order partial derivatives, this, and this u and v satisfies the Cauchy-Riemann equations, equation 1, equation 2, then we can say that the function f of z that is equal to u plus vi is analytic in some domain D. So we have these two conditions. The first one is known as necessary condition, and the second one is known as sufficient condition for analyticity. So let's talk about one example, then you will understand whether a function is analytic or not. So here, let's say, for example, we have a function f of z equals z squared plus z. So our target is to understand whether this function satisfies Cauchy-Riemann equations or not. Or the question will be, we have to check whether this function f of z is analytic or not. We can also say whether this function is holomorphic or regular or not. So we can think about in many ways, but the steps are same. So the first step is we have to find the real part and imaginary part of the function f of z. So we know that w equals f of z can be written as u plus vi, where u and v can be the functions for x comma y. So in first step, what we will do, in left side we have f of z. So where we have f of z, we are writing u plus vi, and the right side is z squared plus z. It is same. So we also know that z is x plus yi. So we can also think about xy forms in right side. So when we have z, let's plug x plus yi. So z squared, that means x plus yi is squared, plus z, that means x plus yi. So in left side we have u plus vi. On right side we can now do some simple calculations. So the first part is going with a plus b whole squared formula. So that is x squared plus 2xyi plus y squared I squared. And we have also x plus yi. So now again we have u plus vi. So x squared plus 2xyi. We have y squared, I squared. So we know that I squared is -1. So we can write negative y squared plus x plus yi. And in next step, we can group the real parts and the imaginary parts. So this is x squared this is y squared, this is x. In these three terms, we don't have any I. So we can group these three terms. That is x squared negative y squared plus x. And the remaining terms are this and this. So we can group the 2xyi plus yi. So we can write x squared negative y squared plus x. And since I is present in both terms, so I can be factored out. So we have 2xy plus y. So this is equal to u plus vi. So now we can understand that u will be this part and v will be this one. So that means now we are going to equate the real parts and imaginary parts from both sides. So equating the real part and the imaginary part. So we are getting u equals x squared negative y squared plus x, and v equals 2xy plus y. So this is our first step. Whenever we have a function f of z, we can find the real part of that function, which is u, and we can also find the imaginary part of that function, known as v. So you can remember that u and v can also be written as u of x comma y, v of x comma y. But for simplicity, we are skipping this. We are just writing u and v. From right side of these two functions, we can easily understand that this u and v are function for x and y. So we can just write u and v. So that means we are going to check whether this function f of z satisfies Cauchy-Riemann equations or not, or whether the function f of z is analytic or not. So for having the Cauchy-Riemann equations, we need at first u and v. So already u and v are in our hand. So u equals x squared negative y squared plus x, and v equals 2xy plus y. So now we know that the Cauchy-Riemann equations are du dx dv dy, du dy negative dv dx. So these two equations are known as the Cauchy-Riemann equations. This is the first equation and this is the second equation. And here du dx dv dy, du dy dv dx, all are denoting the first order partial derivatives of u and v. So here, let's find du dx, du dy, dv dy, dv dx. Then we can check whether these two equations are satisfied or not. So we have u. So let's find du dx and also du dy. We will also find dv dx and dv dy. So we are differentiating u in terms of x. That means x is variable, but y is constant. So we are differentiating u in terms of x. So this is u. So the u function is x squared negative y squared plus x. So whenever we are differentiating in terms of x, then y is constant. So you can remember the formulas or rules of differentiation. If we have the derivative of sum, then we can separate and find ddx of f plus ddx of g. That means the derivative of a sum is the sum of the derivatives. I mean to say that suppose we have ddx of u plus v plus w. So in that case, all these are summation terms. We may also have subtraction term, u plus v negative w. So what we can do? We can separate all the terms and find the derivatives. So ddx of u plus ddx of v negative ddx of w. So this is what we know from ordinary differentiation. So same concept will be applied here. So that means we have x squared negative y squared plus x. So we can expand as ddx of x squared negative ddx of y squared positive ddx of x. Derivative of x squared in terms of x, we know it is 2x. Negative derivative of y squared in terms of x. So we are differentiating in terms of x. This is partial derivative. So y is constant. So differentiation of any constant will be obviously 0 plus differentiation of x in terms of x is 1. So finally, du dx is 2x plus 1. This is what we have found, du dx. Let's find similarly du dy. So dy of u, and the function u is x squared negative y squared plus x. So this time we are differentiating in terms of y. So that means x is constant. So again, we can separate all these terms because we have summation or subtraction. So using this rule, we can easily express. But let me do this time directly. So derivative of x squared in terms of y will be 0. Negative derivative of y squared in terms of y will be 2y. Derivative of x in terms of y will be 0 because x is constant. So finally, we have found du dy equals negative 2y. So now the time is to find dv dx and dv dy. So we are going to differentiate v, and the v function is 2xy plus y. So let me this time separate. So ddx of 2xy plus ddx of y. So we are differentiating in terms of x. That means y is constant this time. So 2 and y will be pulled out. We have ddx of x only. And derivative of y in terms of x. So y is constant. So derivative of constant will be 0. So finally, we have here 2y, ddx of x is 1. So 1 times 2y is 2y. So we have found dv dx. Similarly, let's find dv dy. So we are differentiating v in terms of y. V function is 2xy plus y. So here, again, using this rule, we can separate, or we can write directly. But let me separate. So dy of 2xy, dy of y. So here, we are differentiating in terms of y. So x is constant, 2 is also constant. So 2x can be pulled out. So dy of y. And here, dy of y. So derivative of y in terms of y is 1. And here, dy of y will be obviously 1. So finally, we have found 2x plus 1. That is dv dy. So this is our second step. In first step, we have expressed the function f of z in terms of u and v. And in second step, we have found all the first order partial derivatives du dx, du dy, dv dx, dv dy. So let's check whether Cauchy-Riemann equations are satisfied or not. So the Cauchy-Riemann equations are here. Du dx equals dv dy, du dy equals negative dv dx. So for our function, what is du dx? It is 2x plus 1. Let's also find dv dy. So where is dv dy? This is this one. It is also 2x plus 1. So that means we can say that, yeah, the first equation of Cauchy-Riemann is satisfied because left side and right side are same. So let's find du dy this time. So where is du dy? It is negative 2y. And dv dx, so dv dx is 2y. So don't forget that we have negative sign before. So let's write negative here. So now we can see that in left side we have negative 2y, in right side we have also negative 2y. So that means the second equation of Cauchy-Riemann is also satisfied. So if both the first equation and second equation are satisfied, that means Cauchy-Riemann equations are satisfied, then we can say that the function f of z is analytic. So the function f of z, z squared plus z, it is analytic. And whenever we have mentioned the definition of entire function, then we have understood that any polynomial function will be analytic, and that polynomial functions are called entire function. So this is how we can prove whether a function is analytic or not, whether a function is satisfying the Cauchy-Riemann equations or not. So again, we are going to take a function f of z equals e power z. So this is our function this time. We need to check whether this function satisfies Cauchy-Riemann equations or not, or we need to check whether this function is analytic or not. Our first step is to find u part and v part. So we can easily write f of z as u plus vi. And on right side, we have e to the z. So we know that z is x plus yi. So we are writing like this. Our target is to separate the real and imaginary parts. So u plus vi. Now we need to simplify this one so that we have u plus vi. So whatever form we have in the right side, that is not in u plus vi. So that means we need to think about the property of exponential function. So we know that e to the x plus y can be written as e to the x times e to the y. So using this property, we can write here e power x times e power yi. We have used this technique. Now, we know Euler's identity, that is e to the I theta, that is cosine theta plus I sine theta. We know this one also. So in next equation, we are going to write u plus vi equals e to the x times. Here we have e to the I y. Compare with e to the I theta. So cosine theta plus I sine theta. So that means e to the I y cosine y plus I sine y. So our target is to have u plus vi form on the right side. So still we don't have that form. So we can again simplify. So that means we can write u plus vi equals e to the x cosine y plus I e to the x sine y. That means we have found the real part and imaginary part. So let's equating the real and imaginary part. We have u equals e to the x cosine y, v equals e to the x sine y. So we have found u and v. U is e to the x cosine y, v is e to the x sine y. First step is done. Now we have to find du dx, du dy, dv dx, dv dy. So we are targeting for the first order partial derivatives. Let's find du dx, that is d dx of e to the x cosine y. That means we are differentiating in terms of x, so y will be constant. So cosine y will be constant. So cosine y can be pulled out. So just we have d dx of e to the x. So cosine y, and now we have d dx of e power x is e power x. So finally we can write e to the x cosine y. That means this is du dx. Similarly, let's find du dy. So here we are differentiating in terms of y. So x will be constant. Since x is constant, the total part e to the x is also constant. So we can pull out e to the x before the derivative sign. So d dy of cosine y. So here e to the x. Now we know that differentiation of cosine y in terms of y is negative sine y. You know this formula. So finally, we have negative e to the x sine y. This is du dy. So up to now, we have found du dx, du dy. Let's try to find dv dx and dv dy similarly. So here we have v, that is v equals e to the x sine y. So first dv dx, that is d dx of e to the x sine y. So again, we are differentiating in terms of x. That means y is constant. So sine y is also constant. So sine y is taken before. So d dx of e to the x. Now sine y. So differentiation of e to the x is the same one, e to the x. So that is e to the x sine y. So this is dv dx. Let's find similarly dv dy. So d dy of e to the x sine y. Now we are differentiating in terms of y. So x will be constant, and therefore e to the x is also constant. So e to the x is taken before. So d dy of sine y. Now e to the x. So the derivative of sine y in terms of y is cosine y. So we can write that dv dy equals e to the x cosine y. So step 2 is also done. In step 1, we have tried to find u and v. After step 1, we have found all the 4 first order partial derivatives, that is du dx, du dy, dv dx, dv dy. Now in step 3, this is the time to check whether Cauchy-Riemann equations are satisfied or not. So we know that Cauchy-Riemann equations are du dx equals dv dy and du dy equals negative dv dx. So let's verify whether these two equations are satisfied or not. So first of all, what is du dx? This is e to the x cosine y. So in left side, we have this one. On right side, we need to have dv dy. So where is dv dy? It is this one. It is also found to be e to the x cosine y. So in left side and right side, we have the same terms. So that means the first equation is satisfied. Let's have a look on du dy. So du dy is negative e to the x sine y. We have a negative sign on the right side, so we are writing negative first. So let's collect dv dx. So dv dx is positive e to the x sine y. So e to the x sine y. So we can understand that in left side we have negative e to the x sine y, and on right side negative positive is negative e to the x sine y. That means both left side and right side are same. So it means second equation is also satisfied. So since both first equation and second equation are satisfied, That is, the Cauchy-Riemann equations are satisfied. So the function f of z equals e to the z is analytic. So it is done. We can also say the function is holomorphic or regular. Besides Cauchy-Riemann equations in rectangular form, we have Cauchy-Riemann equations in polar form also. So again, we have the function f of z equals u plus vi. But since we are dealing with polar form now, so this time u is a function of r comma theta, v is a function for r comma theta. So whenever a function is written as polar form, then that function will be analytic if it satisfies the Cauchy-Riemann equations in polar form. So the Cauchy-Riemann equations in polar form are written as this way, that is du dr equals 1 over r dv d theta. And the second equation we have, it is dv dr equals negative 1 over r du d theta. So that means again we have the 4 first order partial derivatives. Try to remember the equations that are in polar form. In rectangular form we had du dx equals dv dy, du dy equals negative dv dx. So this is Cauchy-Riemann equation in rectangular form. But here we have the Cauchy-Riemann equations in polar form. So this is the difference between polar and rectangular forms. So the process is same. We have to check whether a function is analytic or not. And we can also say whether the function satisfies Cauchy-Riemann equations or not. So for example, let's take a function f of z that is equal to z to the power 5. So we have taken a function z to the 5. This is a polynomial function, 5th degree polynomial function. We want to check whether this function satisfies Cauchy-Riemann equation or not. We want to check whether this function is analytic or not. So whatever we have done in previous problems, we know that f of z can be written as u plus vi. And on the right side, we have plugged z equals x plus yi. So this time we have z to the 5, so x plus yi power 5. So there is a difficulty here that we know what will be a plus b squared formula. We know a plus b cubed formula. We perhaps know a plus b power 4, power 5, power 6 by using binomial theorem. But it is getting difficult to simplify. That's why we need the polar form here. So if we apply polar form instead of rectangular form, the problem will be easier. So this time, instead of x plus yi, we know that z is r e to the I theta. So let's plug this one this time. R e to the I theta power 5. So now we know that there is a property. If we have a times b power m, then we can write a power m, b power m. So a times b to the m equals a to the m times b to the m. So you can think about this is r and this is e to the I theta as a times b. So in left side we have u plus vi, on right side we must have also u plus vi form. So first of all, what we can do, we can apply this property a b power 5. So a power 5 times b power 5, that is r power 5 times e to the I theta power 5. So u plus vi equals r to the 5, and now again we can simplify by this way. That is, if we have e to the m power n, then we can write e to the m times n. So here we have e to the I theta power 5. So why not we can write e to the I 5 theta. Now we are writing u plus vi equals r to the 5. So again we can apply Euler's identity, e to the I theta, that is cosine theta plus I sine theta. So think about 5 theta as single theta. So that means we can write cosine 5 theta plus I sine 5 theta. So that means we can easily simplify now. R to the power 5 cosine 5 theta plus I r to the power 5 sine 5 theta. So this is equal to u plus vi. So now you can easily see that whatever form we have in left side, we have the same form on the right side. That is, in left side we have u, then plus, then vi. On right side we have u plus v times I. So that means we have found u and v. So equating u and v, we are getting u equals r to the 5 cosine 5 theta, and v equals r to the 5 sine 5 theta. So let's have a look on the first and second equations of Cauchy-Riemann that are in polar form. So we need to find du dr, dv dr, du d theta, dv d theta. So that means this time we have to differentiate u and v in terms of r and theta separately. So we have u equals r to the 5 cosine 5 theta. So let's find this one, du dr. Then we will find du d theta. So du dr, that is, we are differentiating u r to the 5 cosine 5 theta in terms of r. So have a look here. We are differentiating in terms of r. So except r, other variables are constant. So that means r is variable, but theta will be constant. So since theta is adjacent to 5 theta and we have cosine 5 theta, so this total part is constant. That means this can be pulled out before. So it is cosine 5 theta d dr of r to the 5. So cosine 5 theta, differentiation of r to the 5 is 5 r to the 4, because we know that ddx of x to the n is nx to the n negative 1. Using this property, we can write r to the 5, its derivative will be 5 r to the 4. We have found 5 r to the 4 cosine 5 theta, that is du dr. So the first part has been found. Let's similarly find du d theta. So here we are going to differentiate in terms of theta. The function is same, r to the 5 cosine 5 theta. So this time we are differentiating in terms of theta. That means r will be constant and therefore r to the 5 is also constant. So it can be pulled out. So r to the 5 d theta cosine 5 theta. So r to the 5. Now derivative of cosine 5 theta, it will be negative 5 sine 5 theta. So this is by the formula ddx of cosine ax equals negative a sine ax. We know this formula. ddx of cosine ax, its derivative will be negative a sine ax. So derivative of 5 theta, negative 5 sine 5 theta. Think about 5 as a. You will get the derivative. So now we have found du d theta, that is equal to negative r to the 5 sine 5 theta, and we have 5 here also. So the second part is also found. Now similarly we have to find dv dr dv d theta. So here is v, which is equal to r to the 5 sine 5 theta. So here let's first find dv dr. So d dr of v, that is r to the 5 sine 5 theta. Again, we are going to differentiate in terms of r. So theta will be constant, that means sine 5 theta is constant. So that is sine 5 theta can be written before. So we have ddr of r to the 5. So sine 5 theta r to the 5, its derivative will be 5 r to the 4. So finally we have 5 r to the 4 sine 5 theta. This is dv dr. So that means we have found also this one. Similarly, let's find dv d theta. So dv d theta equals d theta of r to the 5 sine 5 theta. So this time we are differentiating in terms of theta. That means r and r to the 5 will be constant. So r to the 5 is written before the differential operator. So d theta sine 5 theta. So here we have r to the 5. And now we have to find this derivative. So what will be the derivative of sine 5 theta? We know ddx of sine ax, that is equal to a cosine ax. So similarly, derivative of sine 5 theta will be 5 cosine 5 theta. So we have finally 5 r to the 5 cosine 5 theta. Let's recall the Cauchy-Riemann equations in polar form. So we know that the Cauchy-Riemann equations in polar form are du dr equals 1 over r dv d theta. And dv dr equals negative 1 over r du d theta. So let's check whether these two equations are verified or not. So let's first look at this one, du dr. This is here. We have found 5 r to the 4 cosine 5 theta. On right side, don't forget that we have 1 over r already, and now we need to locate dv d theta. So dv d theta is this one, that is we have 5 r to the 5 cosine 5 theta. So if we simplify the right part, we have 1 over r, 5 r to the 5 cosine 5 theta. So r and r to the 5 can be simplified in a way that it will become 5 r to the 4 cosine 5 theta. So that means the left side and right side are same. So the first equation of Cauchy-Riemann is satisfied. Let's have a look on the second equation. So dv dr. So where is dv dr? It is this one, 5 r to the 4 sine 5 theta. On right side, we have already negative 1 over r from the equation. And let's look at du d theta now. So du d theta is this one. We have negative 5 r to the 5 sine 5 theta. So on right side, if we simplify, we are getting negative, negative, positive. R to the 5 in numerator, and in denominator we have r. So it is becoming 5 r to the 4 sine 5 theta. So on left side we have 5 r to the 4 sine 5 theta. So that means on both sides we have positive quantities. That means the second equation is also satisfied. So finally we can say that the function f of z is analytic. So this is how we can check whether a function is analytic or not. So let's talk about the last content, that is known as harmonic function. So first we have to understand what is the definition of harmonic function. So a function will be harmonic if it satisfies the Laplace's equation. So again, we have mentioned another term, that is what is Laplace's equation. So for now, you know that any function w equals f of z can be written in u plus vi form. U and v both can be function of x comma y or r comma theta. Now this u and v has a property. So if a function f of z is analytic, then it is true that u and v will be harmonic function. So if u is harmonic, then v is called the conjugate harmonic. If u is harmonic, then v is also harmonic. So here, now we have to understand what is the definition of harmonic function. So a function will be harmonic if it satisfies the Laplace's equation. So now we have to know what is Laplace's equation. This equation is named after mathematician Pierre-Simon de Laplace. So what is Laplace's equation? Let's say we have any function. We can say this one as pi, P-H-I. This is the symbol which is known as phi or phi. So let's say we have this function phi. From this function, we can find d phi, dx, d phi, dy, if this function phi is a function for x comma y. So this is the first order partial derivatives. We can also find the second order partial derivatives. That means we are differentiating again. So the second order partial derivatives is denoted by this one. So whenever we have this second order partial derivatives for this function phi, we can add these two quantities. It may become 0. So whenever the second order partial derivatives for this function is equal to 0, then we know that is as Laplace's equation. So we can say again that any function phi of x comma y will be called harmonic if it satisfies the Laplace's equation. The second order partial derivative with respect to x plus the second order partial derivative of this function with respect to y. If the summation of these two becomes 0, then we can say that this function is harmonic. And the equation that I have written here is called the Laplace's equation. So this is the general definition. So here for f of z, we have u and v. So we have mentioned that if f of z is analytic, we can say u and v will be harmonic functions. If u is harmonic, then v is also harmonic. So since u and v are harmonic function, so it is obvious that both u and v will satisfy the Laplace's equation. So for u, we can write the second order partial derivative of u with respect to x plus the second order partial derivative of u with respect to y equals 0. So u of x comma y will be harmonic if it satisfies the Laplace's equation. So when we have phi, we are just plugging u. Similarly, the function v will be harmonic if the second order partial derivative for v in terms of x plus the second order partial derivative of v in terms of y becomes 0. That means v satisfies the Laplace's equation. Then we can say v is harmonic. So we have u and v. In general, we can say any function phi. So this is the condition or definition for harmonic function. So suppose we have u. So what will be the procedure to find v? V is known as the harmonic conjugate of u. So let me solve one problem directly, then you will understand. So let's say we have a function u which is a function for x comma y. So let us consider that u is equal to 2x times 1 negative y. So we have this function. Our first target is to check whether u is harmonic or not. If anyhow we can prove that u is harmonic, then it is a must that there will be v of x comma y. And then finally, if we add u plus vi, we will get the main function back, f of z. So this is our target. So first we have to verify whether a function u is harmonic or not. That means, in other words, we can say u satisfies Laplace's equation or not. We have to check. So suppose u is harmonic. Then we need to find the conjugate harmonic of u. So find the harmonic conjugate of u, which is known as v of x comma y. So after having u and v in our hand, we can easily find f of z, that is u plus vi. So using the concept of harmonic function, we can also find the derivative of the function, but that is not our concern. Our target is to find f of z only for this time. So let's start from the very beginning. We want to check whether u is harmonic or not. So u function is 2x times 1 negative y. So if u is harmonic, then u will satisfy this equation, which is known as Laplace's equation. So you can understand that this defines the second order partial derivative of u in terms of x, and this is the second order partial derivative of u in terms of y. So that means at first we need to find first order, then second order derivative. Before this, we can simplify our function u. It is 2x negative 2xy. So first of all, we are differentiating u in terms of x. So again, partial derivative is being applied. So ddx of 2x negative 2xy. So we are differentiating in terms of x. So y will be constant. So I am writing directly here, derivative of 2x in terms of x is 2. Negative 2 and y will be constant. So 2y. Now derivative of x is 1. So 1 times 2y is 2y. So this is du dx. You can see we have to find the second order partial derivative. That means we have to differentiate this function again. So we are differentiating again, that is the second order partial derivative of u in terms of x, which means we have to differentiate this function, not u. We have to differentiate the first derivative function. So it is 2 negative 2y. Again, we are differentiating in terms of x, which means y will be constant. So you can see that derivative of constant 2 in terms of x is 0. Y will be constant. So again, this term is also a constant. So derivative of a constant is 0. So that means we have 0. So that means we have found the second order partial derivative of u in terms of x is 0. So similarly, we have to find this part. That means first we need to find du dy. So here we have u equals 2x negative 2xy. So let us find du dy. So ddy of 2x negative 2xy. So this time we are going to differentiate in terms of y. So x will be constant. So derivative of constant is 0. Negative 2x is constant. So 2x is pulled out. So derivative of y in terms of y is 1. So finally we are getting negative 2x. So this is du dy. We need to find the second order partial derivative for y. So therefore, the second order partial derivative in terms of y, that is, we are going to differentiate this function. So here we have negative 2x. So since we are differentiating in terms of y, so x is constant. So derivative of constant is 0. So the second order partial derivative in terms of y is 0. So we have found the two parts, this one and this one. So we know what is Laplace's equation. So let's add this first equation, equation 1 and equation 2. So adding 1 and 2, we are getting equals 0 plus 0, that is 0. So that means u satisfies the Laplace's equation. So we can say that u is harmonic. So the first part is done. We are able to prove that u is harmonic. Since u is harmonic, there is also a conjugate harmonic, v. So let's find v. So u equals 2x negative 2xy. So up to now, we have understood that u is harmonic. And since u is harmonic, so we can easily understand that f of z equals u plus vi will be analytic. But still, we don't know what is v. But we can understand that the function will be analytic because u is harmonic. So since the main function f of z is analytic, we can say that this function will satisfy the Cauchy-Riemann equations, that is du dx dv dy, and du dy equals negative dv dx. These are the Cauchy-Riemann equations in rectangular form because we have x and y here. So let's try to find v. So up to now, we have the Cauchy-Riemann equations in our hand. So the first equation is this one, and the second equation is this one. So from the first equation, we can see that we have du dx equals dv dy. This is the Cauchy-Riemann equation, first equation. So what is du dx? Just try to remember that we have already found du dx. So in the first part, we have found du dx equals 2 negative 2y. So let's plug this one here, 2 negative 2y equals, on right side we have dv dy. So our target is to find v. So we are just rearranging dv dy equals 2 negative 2y. So in this step, our target is to find only v. So we can separate v and y. So our target is to find v. That means we can use the concept partial integration. So for now, this concept is new to you, but just like this partial differentiation, whenever we are differentiating in terms of x, then y is constant. Similarly, for partial integration, whenever we will integrate in terms of y, x will be constant. So remember that u function is a function for x comma y. So if we integrate in terms of y, then x will be constant. Let's say we have integration of f of x dx. So this indefinite integral will give us an antiderivative with a constant c. So we know that for this integral we will use a constant c. But since this time x itself a constant, so instead of c, instead of a number, we can think about a function. Let's say g of x is constant. So instead of c, we will write another function g of x that is working as a constant. So okay, now our target is to find v. So for that, first we will integrate in terms of y. So we have dv dy equals 2 negative 2y. So let us integrate. So we have dv dy, and on the other side we have 2 negative 2y dy. So this part will give us v. On right side, we will have integration of 2 negative 2y dy. So integration of 2 in terms of y is 2y. Integration of 2y, that is 2y squared by 2. So since this is an indefinite integral, we can leave a constant c. But don't forget that we are using partial integration concept. So we are integrating in terms of y. So x is constant. So a function g of x is working as a constant. Remember. So we have found v, that is v equals 2y negative y squared plus g of x. So our target is to find v. So 50% task has been completed. We have already v in our hand, but the only unknown that we have here, it is g of x. So let's try to find g of x. So you can remember that first we have worked with the first equation, du dx dv dy. So we have also another equation, du dy equals negative dv dx. So let's work with that one. So we have found v equals 2y negative y squared plus g of x. So the second equation of Cauchy-Riemann says that we have dv dx. So let's differentiate v in terms of x. So you're using again the concept of partial differentiation. So v is here 2y negative y squared plus g of x. So we are differentiating in terms of x. So y will be constant. So derivative of y in terms of x is 0. Derivative of y squared in terms of x is 0. Derivative of this function. So we have a function for x and we are differentiating in terms of x. So its first derivative will be g prime x. So that means we have dv dx equals g prime x. Now from the second equation of Cauchy-Riemann, we have du dy equals negative dv dx. Du dy equals negative dv dx. So you can remember that we have found du dy in our first part. So du dy is negative 2x. It has been found in the first part. So du dy is negative 2x. We are going to plug that part here. So negative 2x equals negative dv dx. Just now we have found dv dx is g prime x. So this is g prime x. So finally, you can see that on both sides we have negative sign. So we can omit or skip that negative sign. So we have g prime of x equals to x. So finally, you can understand that this time, just to find this unknown g of x, we have to integrate g prime of x. So that means, let's integrate again g prime of x in terms of x. So on both sides, we are integrating in terms of x. So remember, whatever function we have here, this is only for x. So this time, we can think about a constant as a real number. So you know that g prime of x dx, which is also known as dg dx dx, that is, we have finally dz. So integration of 1 in terms of g, that is g. So we have found g. So g is a function of x, so we can write g of x equals. So on right side, 2 is constant, 2 can be pulled out. So we have integration of x dx. So we can write g of x equals 2. So integration of x in terms of x, we know it is x squared over 2. So again, we have an indefinite integral. But remember, this time there will be only a constant. This is just a number. It is not a function. It is just a number. So here, g of x equals 2, and 2 can be simplified. So here we have x squared plus c. So our v is here. The only unknown that we have, g of x, it is already in our hand. So let's plug g of x here. So that is 2y negative y squared plus g of x. is x squared plus c. So this is our v. So we have found our result. So in some textbook, you will see that there is no c. So we can escape c. So we can also write that v is 2y negative y squared plus x squared. So our second part is also done. We have found the conjugate harmonic function v. This is our second part. Now let's find f of z, that is u plus vi. So our third part is to have f of z. So we know that f of z is u plus vi. So now we can input u and v. So we know that we have u as 2x negative 2xy plus v. V is this one, 2y negative y squared plus x squared.